lecture, which will be given by Professor Enrico Arbarello from the University of Rome, La Sapienza. Professor Arbarello is well known for his contributions to several branches as Riemann surface, curves and moduli of curves, abelian and Jacobian varieties, KdV equations, infinite dimensional linear algebras, and he has also been a visiting professor or a distinguished visiting professor at several first-rank universities, such as Harvard University, MIT, École Polytechnique, Columbia University, where he got his PhD from. And he has also addressed at several important mathematical meetings, like AMS symposiums and the International Congress of Mathematics in Berkeley in 1986. In the same year, he got a medal from the Italian National Academy of Science, and he's so a distinguished member of that academy. So, okay, that's enough. So please, Professor Arbarello. And the title of his talk is Curves and Their Moduli.
You didn't hear that it is a great pleasure to be here. And you didn't hear that I'm very thankful for this invitation, so let me repeat that. I was saying that I'm starting from what apparently would seem long ago, but from a certain point of view it's not. So Apollonius operated in Pergas in the year more or less 262 BC. Pergas is in Turkey right now. So, and see, it's very beautiful near Pergas. And he started a long journey and he went to Alexandria. That was the Hellenistic period. And the entire region was fairly peaceful under the Hellenistic influence. And he went to study, Euclid died a few years before, he went to study to Alexandria. Where there was a library, but especially where there was a school of Euclid, because Euclid was based in Alexandria. And of course, Euclid started, as we know, the geometry of lines, points, and Apollonius started with conics, looking at conics as a section of the cone, so in a completely synthetic way. He wrote 387 propositions. Of course, I mean, even the simplest one, that a line intersects a conic in 2 points, or 2 conics intersect in 4 points, mostly. Or, for instance, that there are at most 8 circles that are tangent to 3 given circles. Here, the 3 circles are in red, and I just draw 2 of the possible 8 circles that are tangent. Everything synthetically. I mean, if we had to have an idea of why there are at most 8, I mean, it's obvious, right? Because a circle depends, I mean, you write down the equation of a circle, so it's x minus a squared, say something like that. There are 3 parameters. So we are in R3. The condition to be tangent is a quadratic condition, so we have a quadric in R3. So we have 3 quadrics in R3. 3 quadrics in R3, so 2 quadrics intersect in a curve of degree 4, and then 3 quadrics in 8 points. what we just did was more or less 1,000 years of mathematics. Because first of all, we introduced the notion of moduli. That is, without thinking it, we are thinking at a conic as a point in a space. This means moduli, parameters. So A, B, and C for us is a conic, is a circle. And then we have intersection. And we have to count intersection. So, and first of all, I mean, we even expressed this as an equation. So it took a long time. For instance, to give you an example of something that happened, I mean, it is amazing that it took a long time, but Newton and Leibniz were reading Apollonius avidly. They were learning from Apollonius. This happened 1,800 years later. So it was good mathematics that stayed. So to give an example of computation of that kind, much later, Michel Charles proved that there are, you see, that's much more difficult, 3,264 conics that are tangent to 5 given conics. Of course, I mean, Schubert was almost a maniac. I mean, so he became so good at it. And it's, where was that? Ah, here. Okay. So he proved this kind of theorem. But of course, I mean, Schubert and Charles could not do what they did before without the work of Descartes, who translated in algebra the geometrical questions, the geometrical problems in equations. So the point is, this was the real revolution, I mean, to translate it into equations. So to see the coefficients of the plane curve, for instance, as the parameter of the plane curve. So the line, the conics, and then more complicated, for instance, a cubic. But of course, when you start intersecting these geometrical configurations, these curves, there are, of course, missing intersections, things that you don't see, parallel lines, and things like that. So there are two sources of missing points, and so to find missing intersection, we have to go back to painters. It was Dürer and Leon Battista Alberti. Actually, here I should. Yeah, I forgot to write this. There is also Piero della Francesca. I cannot miss his name. He's more or less equal to 90. And this is De Prospettiva Pingendi. So he wrote this book. Piero della Francesca was extremely good. Vasari, when he writes about him, Vasari was a biographer of artists in the 16th century, and he wrote that Piero della Francesca was an amazing mathematician. And but his job actually to earn money, he's translated from Greek and Latin in Rome for the church. So they introduced projective geometry, so they started finding this missing intersection and understanding that, in fact, a line and the parabola intersect in 2 points. One of them is at infinity. The second source of missing intersections is given by complex numbers. So there, of course, there are both Girolamo Cardano, but especially Raffaele Bombelli. Raffaele Bombelli essentially introduced the complex number I, the square root of -1. And Cardano was using it. Also, Bombelli was more systematic about it. Cardano was also, he was a strange guy. He was a very violent guy. He was a compulsive gambler. He killed someone. But then he also had the chair of mathematics in Pavia. He was a very complex personality, very violent. I guess, I mean, just for his gambling, he studied also some mathematics. I mean. So Raffaele Bombelli was an engineer, and Cardano was a medical doctor at the end. So none of them. So while Apollonius was a mathematician, all the people that we are encountering now were not mathematicians. Cardano was a medical doctor, ended up being a medical doctor. Bombelli was an engineer. He drained all the swamps in Colle Valdelsa near Siena. That was his job, and he was very good at it. And when, for bureaucratic reasons, he was waiting for permission for do that job, he was writing a treatise in algebra. And in fact, in this treatise in algebra, he was very much inspired by Arab mathematician, of course, because this is Umar al-Khayyami. It's around 1000. He lived up to he was 90 years old when he died. And what the monastery did in Europe for the literature, the Arabs did for the mathematics. That is, we know Apollonius because of these guys who were at the same time familiar with the Indian mathematics and with the Greek mathematics. So this is, they were studying this, and they were using the complex number, in a certain sense, like we are using the functional integral without knowing what it is. In a certain sense, it was Carl Wessel, much later, who did something which now seems to us totally natural, that is to think at a complex number as a point in the plane. And Carl Wessel was a cartographer. That was his job. So there is, in a certain sense, no wonder. So curves started appearing as now complex solutions of polynomial equations. But still, even after Wessel, even when Blücher was operating, or Schall, the complex solutions were thought as something really imaginary or strange. I mean, of course, it was Riemann who revolutionized everything, because he took the curves out in thin air, no longer in P2. So the curve that we are, what is that? The curve that we are seeing C2 is just one of the possible incarnations of a Riemann surface. The two complex coordinates are simply two meromorphic functions on the Riemann surface. So what we have really to look is an abstract Riemann surface. But then, when we are looking at an abstract Riemann, when we were looking at the polynomial equation, immediately the parameters were apparent because they were the coefficient of the polynomial. So we could identify a curve with a point in real space or complex space or projective complex space. Now, what do you do with the Riemann surface that lives in thin air, lives in empty space? So this is the picture of a Riemann surface. Now ZW are two meromorphic function. But now the Riemann surface, of course, has parameters because the complex structure varies. So let me say two words about it. But before maybe saying this, let me give some of the pictures. Of course, we have lines and conics, and these appear in the Riemann, from the Riemann point of view as a sphere. There is a cubic. The quartic is genus 3. So there is this first invariant, which is the genus, and there is a formula that Blücher, that Klebsch found of the genus. but he did not have this picture. I mean, he thought of this formula as deficiency of maximum number of double points. In fact, okay, so there is this formula for a curve of degree d, plane curve, for instance, like this Fermat curve. The genus, or the number of folds of the corresponding Riemann surface, is given by this formula, d minus 1, d minus 2 divided by 2. And maybe also one more picture is needed. Sometimes we see on a curve singularities. And what one should see is that, for instance, in this case, here I'm saying that a plane irreducible curve of degree d has at most d minus 1, d minus 2 double points. So let's take, for instance, a cubic. The cubic has just maximum, reducible cubic, maximum number of 1 double point. So what we should see instead of this cubic, so the corresponding Riemann surface living in thin air is just a surface. And what happens is that when you try to force this surface in the plane by having some plane incarnation of this surface, the plane is, I mean, it's too small. I mean, you have to generate a singularity. Of course, I mean, the same Riemann surface, if you put it in a bigger space, where there is more space, so to speak, is a non-singular one. For instance, already in 3 space, it's a nice non-singular one. But if you want to force it into space, then some singularities are forced. So what you see is this picture, in fact. So what are now the parameters for these Riemann surfaces? Parameter for these Riemann surfaces, well, in genus 0 there is not much to say. I mean, it's the Riemann sphere, and that's it. In genus 1, the picture is more interesting. In genus 1, we have tori, and it is an exercise in one complex variable to see that, in fact, there is just one parameter for the complex structure. So what we have to think about in this term is, before, when we were thinking at plane curves, so in the first approximation, we were thinking, well, 2 curves are equivalent if we can transform one into the other by a projective transformation. Then, of course, we could have more general transformation like the Cremona transformation, the notion of birational transformation, and so on. For a Riemann surface, the notion is analytical equivalence. So analytical equivalence maintains angles, and so immediately you see this picture. If you change the angle, you change the conformal structure. So there is one parameter, it's this vector tau. For surfaces of Riemann surfaces of genus bigger than 2, so one takes this big set, which is genus surfaces modulo equivalence, modulo isomorphism. This is MG. This is called the moduli space, or the parameter space for Riemann surface. And it is, I mean, a very important fact that this, in fact, is an analytic space with very mild singularities, and it has dimension 3g minus 3. Here g is greater or equal than 2. So let me give an idea of why this is true. It's not difficult. Let's look, first of all, at the case of annuli in C. So an annulus is just, okay, it's an annulus. And I guess I put the picture in the phone. Okay. This annulus has one parameter. You can fix one of the circle to be 1, and the other one R. R is the parameter for the annulus. So 2 annuli are analytically equivalent if R is the same, if and only if. Then there are pans, which is the next picture. And this depends, so this is the pan, pair of pans, which can be drawn as a circle minus 2 inner circles. And this depends on 3 real parameters. 3 real parameters that are exactly the length of these three circles. So when you have a Riemann surface, you have a pentacomposition. In fact, it's very easy to prove that. I mean, this, of course, is not the only way to make a pentacomposition. There are many ways. But in any case, you can always decompose in 2G minus 2 pans. 2G minus 2 pans have each has three circles. So, but then you have an identification. So you have 6 real parameters given by the length of the pans, and then 6 angles that tells you how to glue the pans. So in case of genus 3, so 6 and 6 is 12. You have 12 real parameters, and therefore 6 complex parameters. So this is the count that can be made in general. Now, the point is, okay, so we are looking at this space. It's a space of dimension 3G minus 3. That, as I was saying before, you can consider as a smooth variety of dimension 3G minus 3. The singularities are very, very simple singularities. Singularities that are a quotient of C3G minus 3 minus modulo finite group. So something very simple. So the problem is, well, you see, before, when we were trying to solve a enumerative question, for instance, for circle, what we had was the intersection theory in R3. That is, we had to say how 3 quadrics intersected for that case. So in this case, we have to do the intersection. We have to start with the intersection theory for this space. So, but what does it mean, the intersection theory for this space? So in order to do this, of course, we go back to Élie Cartan, and we start to see how do you do intersection theory on a variety, on a d-dimensional variety. So the way of doing intersection theory on a d-dimensional variety is by differential forms. So you look at differential forms on the variety, so that are locally expression of that type, where x1, xd are local coordinates on V. And there is, of course, the theory, the Delam theory, the Élie Cartan theory of closed form and exact form. So you have the differential, you have closed form and exact form, and the cohomology are just closed K form divided by exact K form. So this is the cohomology. This is where, in a certain sense, one place where the intersection theory happens, and it happens in this way. The fact is that this object is, in fact, if you add them up, if you add all these cohomology groups, this is a ring. The ring has a very natural structure. That is, the product structure is nothing else than the wedge product of form. And the fact is that this product structure has geometrical interpretation is due to Poincaré and Poincaré duality. The idea is simple and beautiful. That is, you want to translate properties of subvarieties, like W, or like W intersect another one, W prime, into properties of forms. So the first thing that you see is that when you have a subvariety, you can integrate over it K form. So Poincaré had this idea, is that there is a canonical way to associate to a subvariety a form of the complementary dimension, which has the property that integrating a K form on that variety is like integrating over all variety that form omega W, which is called the Poincaré dual of W, wedge phi. So this is the basic tool for intersection theory. The basic tool for intersection theory is Poincaré duality. That is that canonical way of associating to a subvariety a form. So this is a big step, a step of the kind of Descartes. That is, you translate now intersection theory analytically, in analytical terms. So So suppose, for instance, that you have in this ambient variety V n subvarieties, and that these n subvarieties intersect in a finite number of points. Then the basic result is this, is that W1 intersected Wn, the number of points, is given by the integral of the wedge product of the Poincaré duals of those. So this is the way of translating intersection theory into an analytical. Okay, so now, for instance, back to Apollonius. I mean, if you want to intersect two lines, you take the Poincaré dual of one line, Poincaré dual of the other line. They are the same because of the Poincaré duality. You intersect it, you compute it, which is not completely trivial. I mean, it's an exercise, and you get one. And the same thing you get with the conics. Okay. So if you want to do now projective geometry, for instance, in P2, or let me do everything in Pn. So what you notice is that the only thing that you have to know is how lines intersect. So this is completely back to Euclid. How line intersects tell everything. And in Pn is how hyperplane intersect. Psi is just the Poincaré dual of a hyperplane. And how psi intersects with itself tells everything about the cohomology, about the intersection theory of Pn. And this is the cohomology of P2, P3, Pn. And of course, it's an interesting observation to know that it pays to take the limit as n tends to infinity, because you get rid of this modulo Pcn of Cn plus 1. And you get a ring which is much better, because this is a polynomial ring. So sometimes it pays to take n that goes to infinity. We will see this. Of course, another important notion is the one of Euler characteristic. So you can triangulate your variety into triangles of various dimensions, and then compute the alternate sum of number of triangles of the various dimensions. This is a basic invariant, which is the Euler characteristic. Sometimes you don't succeed in computing the homology or the homology, but the Euler characteristic you succeed in computing. For instance, for a surface of genus G, the Euler characteristic is 2 minus 2G, and for Pn is n plus 1. These are two examples. Okay, so now there are two problems. One problem is to describe the homology ring of Mg, because this is where the intersection theory happens. And the second one is to describe the intersection theory on Mg. There are two separate problems. Well, the first thing is that, I mean, we talked about missing intersection. Missing intersection, it means that the intersection may go to infinity, so Mg is not compact. So first of all, we have to compactify Mg. So it pays to do two steps. One thing is to pass from Mg to Mgn. It will be immediately apparent why. Mgn is not just Riemann surfaces, but Riemann surfaces plus n points. So you not only let the Riemann surface vary, but you also let the n points vary on the Riemann surface. So you have to add to the 3G minus 3 parameter of the Riemann surface also n parameters of the point wandering around a fixed Riemann surface. The second thing that you have to do is to pass from Mgn to Mgn bar. That is to add something at the boundary. And the something at the boundary are singular Riemann surfaces. And in fact, it is an astonishing fact that only if you add nodes, a priori, I mean, it seems that you have to have all kind of singularities in order to get something compact. But no, nodes suffice. So it is sufficient to add nodes, and you get a compact variety, the compactification of Mg. I also put a few points around why. I mean, so you see, when you try to go to the boundary, so you have a Riemann surface, you go to the boundary, so some cycle is squeezed, and then you get this pinched Riemann surface, then you go to the boundary. But of course, I mean, if you try now to separate, there are two distinguished points over there. So going to the boundary suggests to you that it would have been better if you consider pointed Riemann surface, because in any case, if you go to the boundary, you get pointed Riemann surface. So why not starting with pointed Riemann surface and do the theory for them? So this is why one is doing pointed Riemann surfaces. And in fact, when you see this picture, you see that in a certain sense you should consider all Riemann surfaces of all genera and with all number of points. And Grothendieck understood this. He was the first to understand this. I translated, so this is bad for two things, because my English is not so good and Grothendieck's French is so beautiful. But in any case, so among these modular multiplicities, this is writing in Esquisse d'un Programme in '84. So it's among these modular multiplicities, the one of Mountford-Deligne for the stable algebraic curves, or the stable algebraic curves as curves with nodes, which I denote by M bar G nu, which is a compactification of the open multiplicity M G nu, have exerted on me for 2 or 3 years a particular fascination, maybe stronger than any other mathematical object to this day. But really the object is the system of all the multiplicity MGN. So it has a clear idea. For variable G and nu linked by a certain number of fundamental operations, like operation of filling the holes, gumming mark points, gluing, and the inverse operation, which are the reflection in characteristic 0 for the moment, algebraic geometry of geometrical operations which are familiar from the viewpoint of topological or conformal surgery of surfaces. And after Grothendieck, I would say that it's Witten that really understood also in a very operational way that you had to consider all Riemann surfaces with all points together. This came from very naturally, in a certain sense, from string theory. Here is a picture of a Feynman diagram, and it's another Feynman diagram. And one generally is expanding integrals or partition function in terms of Feynman diagram. And one gets all kinds of Feynman diagram, of course, in this expansion. So if you start instead of a point, which is this red dot, with a little hole, with a little string, the analogous of this Feynman diagram is this, and the analogous of the second Feynman diagram is this. So you get Riemann surfaces. In the first case, you get M04. In the second case, M14. So, oops. And what you have to do, generally, it is natural, at least from the string theory point of view, to integrate over all possible paths, or integrate over all possible Feynman diagram. And here it means integrating over all possible Riemann surfaces. Then, I mean, there is you cut some infinity, which comes very naturally, and then you integrate only on conformal structure of Riemann surfaces, but all genera and all points. So, the question, of course, is what is, the first question I was raising is what is the cohomology? So, one, of course, is trying to imitate the case of projective space, or more generally the case of Grassmannian, which is the next stage where one can compute completely the cohomology, slightly more complicated, but still is a very beautiful picture. So, in fact, it was Mumford who had the idea that the moduli space is not that far from a Grassmannian. So, there are a certain natural differential forms, which I'm now more or less defining. So there exist natural classes psi1, psi(n) in H2 of MGN. These are degree 2 differential forms. So let me maybe explain what this is. These differential forms are like this. I mean, here here is the moduli space. So this is MGN. Can you read here? No, you cannot. No. So I see. So let me go around. So this is MGN. So a point in MGN represents, say, a curve plus n points. This is a modular space. So over MG, so this point, so let's put the curve over it. Something like this. So I put the curve over it. And of course I have also the n points. Okay. Now I let the n points vary. These are marked. So I can take around, for instance, say this is P1, this is P2, and this is Pn. So around this P1, I can consider the circle bundle around this P1. So the tangent and then the circle bundle. So this is a bundle over MGN. So C1 is just the first Chern class of this bundle. C2 is the first Chern class of the bundle of the circle bundle around P2 and so on. So then there are classes. So these are all, since these are circle bundles, these are degree 2 classes. So the picture is very similar up to now to the case in projective space, where you started with, I mean, all cohomology in projective space is given just by a degree 2 class, which is the Poincaré dual of the hyperplane bundle. So here you have these classes. But now it gets more similar to the Grassmannian from the Segre point of view, actually. That is, what you do is that, you see, you have a map from MGN plus 1 to MGN. It means just forget one point. So over there you have Cn plus 1. Here is Cn plus 1. Raise it to the I plus first power here. So you get a form of degree 2i plus 2. Now, in the picture that I draw here, which is no longer there, there was, so this lives upstairs. Here it is. Now you integrate over the fibers. That is, you integrate over two-dimensional thing. So you lower this degree by 2, because this degree was 2i plus 2, and you get kappa I. This is very similar procedure to what you do with the Segre class. So kappa I now live in cohomology of degree 2i of MGN bar. So these are natural classes that are given, like in the Grassmannian. There are all these classes, Psi, and then there are the kappa I's. These are called the tautological classes. And they were introduced by Mumford in 1980. And Mumford conjectured that the stable cohomology of the moduli space, of the open part of the moduli space, here I should put, where is my, bar, sorry. Of the open part of the moduli space was generated by this. And this was a recent, very important result proved by Madsen and Weiss in 2003. So, but I should also mention the name of Harrer and Ulrike Tillman. Harrer contributed to that by saying that the cohomology of the modular space stabilizes, but he didn't know where. And Tillman was very instrumental in the work of Madsen and Weiss. The theorem says that the limit as g tends to infinity of the cohomology is a polynomial ring. What does it mean? It means that if g is very big, recall that these cohomology classes are all of even degree. So this in particular says that stably the cohomology of the modular space is of even degree, like the Grassmannian or like the projective space. So this says that if G is very big, then the H odd with I much less than Z is 0. And similarly here, that the 2i degree part of MGN, of the open part, is the ith degree part of a polynomial ring. one should not get too pessimistic about, in the sense that, I mean, this is not going to be, is never going to be the result for all cohomology. It's a stable result, because Harel and Zagier in 83 proved the Euler characteristic of MGN has this formula, where the important term is the Bernoulli number, zeta of 1 minus 2g, and this Bernoulli number is generally negative, it's almost always negative, meaning that there is odd degree cohomology in the moduli space. So it is an odd degree cohomology that will die when G is very big, but which exists. So for the compact parts, almost nothing is known, few things are known. Of course, if you look at the cohomology of the compactification, not only you have these classes, but also you have the classes of the boundary. So these are, say, loci, the loci where certain things happen. For instance, delta 0 is the loci of curves with one node. Delta 1, 3 is the locus of curves where one is, say, in genus 3, one point is on one side, 3 points are on the other sides, and so on and so on. So with Kornalba, we proved some result in this direction. That is, we proved at least, I mean, the vanishing of the cohomology up to degree 5. Deligne proved that already H11 is different from 0. And we can also prove that H2 is generated by this. And in fact, also H4 was proved by Marziapolito. It's generated by canonical classes. But nothing is known about this method for the closed part. Now, what about the intersection theory? So in the intersection theory, in the Poincaré, from the Poincaré point of view, the intersection means intersecting the Poincaré duals. And these are the canonical classes. So these are the only ones. Of course, we don't know if these are the, actually we are sure that on each MGN there are more classes, okay? So, but still there are these canonical classes, and we would like to know what are these intersection numbers. So the first remark that Witten made in 91 was really along the lines of what Grothendieck intuition was. That is, if you know, this is it's rather remarkable, that is, if you know the intersection of the classes psi, but for all Gn and D1, Dn, all possible things, then this is equivalent of knowing the intersection of the psi and the kappa. So the kappa disappears from the picture. So you only have to know the intersection of the psi. This was the first remark. For the second remark, I have to go back in time. Just a brief. Second remark introduces KdV. Let me recall the basic idea of KdV. It was Scott Russell who discovered the solitary wave in 1844. He was an engineer. And the main feature of the solitary wave is that the area doesn't change under this solitary wave. So there is a conserved quantity, which is this area. And Korteweg and de Vries wrote the equation for this, and in fact, this is this way of writing it shows immediately that this is a conservation law, because this is the derivative of ut is equal to derivative with respect to x. So it means that u, the integral of u, is conserved. So the integral of u is conserved, and in fact, people like Gardner and Miura discovered that there are many other conserved quantities, and it was Lux who understood what the conserved quantities are. The conserved quantities are the eigenvalues of the Schrödinger operator written in terms of u. That is the idea of what Lux understood, that was the real breakthrough, was that the Korteweg-de Vries was a condition for, if you take d square, of course, this delta is d over dx. So if you take the Schrödinger operator varying in time, then this is an isospectral deformation in time if the Korteweg-de Vries equation holds for you. So these were the conserved quantities. And Gelfand and Dickey, this is actually important to write down this equation, had a way of writing all these conserved quantities in a systematic way and in a recursive way. So there is an entire hierarchy of these equations that are expressed as conservation laws. And in fact, this can be also thought of as a completely integrable Hamiltonian system. So the conserved laws are in evolution also. So in fact, it pays to separate the variables and to write each conservation law with a separate variable. So you have a U which depends on infinitely many variables, and you have all these conservation laws. So this is the KDV hierarchy, a generalization of the KDV. So what Witten and Kontsiewicz proved, and Witten conjectured, was that, let me write it here, so that if you take these integrals, the one we are interested in, these, you organize them in an infinite series, and this is just formal series, then this series satisfies the string equation and the KDV hierarchy. So why, let me say 2 words of how, what was the, why this, why? The point is this, is that physicists like Boole, Spencer, Witten had already a clear idea that certain matrix integrals satisfy the KDV equation. So matrix integral is just an integral of expression in the traces of a matrix against the probability measure on the space of matrix, which is essentially e to the trace x squared, where x is a variable matrix. So they knew 2 things about this integral. First of all, that they can be expanded in graphs, and these graphs are 2-dimensional, graphs which have, with respect to Joe Spencer graph, one more information, which is the information of a cyclic order around each vertex, so that are graphs that lie on a surface. So this is the first thing that they knew. They knew that this integral, matrix integral, could be expressed as an expansion in terms of graphs that lie on a surface. The second information was that somehow they were linked to KDV. They satisfied KDV. Experimentally, they saw that it satisfied KDV. Now, it so happens that the moduli space of Riemann surface can be triangulated in terms of graphs. I'm not going into this. And when you triangulate this in terms of graphs, then you express the integral over a moduli space like this as a sum over graphs. This sum over graphs, in turn, can be expressed as a matrix integral. The matrix integral satisfies KDV. This is the idea of the proof of that. In fact, I mean, the point of view of these graphs is, in a sense, complementary to Joel Spencer's point of view. That is, the point is not counting graphs. The point is expressing an unknown quantity in terms of graphs. And in fact, you are never able to count these graphs. But a posteriori, if you know that some equation holds for this infinite series, then you can compute the coefficients. And this is a way of counting graphs, not asymptotically, but on the nose. So this is let me go back to this classical problem of counting the number of plane curves. Remember, we were counting lines through 2 points, conics through 5 points. So the generalization is counting, for instance, one of the result of Schall and some of the result of Schubert, counting the number of plane curves of degree d and genus 0, that is with maximal number of double points, passing through 3d minus 2 points, because in this way you nail it down to a finite number. Okay? So this was something that was computed by Schall, by Schubert. Now, let me make a chart of this. So this is the first case. This is Euclid. This is Apollonius. The conic through 5 points. This is just one. Schall proved that for cubics with one node and through 8 points, there are 12. And Schubert, with all this method, proved that. And of course, now we can prove all these. And this was first proved by Konciewicz. And then, with methods that are closer to Apollonius in a certain sense, by Caporaso and Harris, and Laxdorff-Ellingsrud. And I should mention at the very end that because I forgot to say it before, because I did not write it here, that the computation of intersection number given by Witten and Konciewicz has 2 more proofs, and completely different. One is by, it's a very important result, so more proofs. One is by Okunkov and Pandaripande. And that happens more or less 3 years ago. And then one really amazing proof by Mirzakhani. She just graduated at Harvard with Kurt McMullen, and she gave a beautiful proof of the Witten conjecture in a completely different way, using hyperbolic geometry. And so from that point of view, matrix integral of that is out of the picture, but of course the Corte-Vries equation is still there, and it's still very mysterious. And there is no algebra geometric proof up to now.